Can somebody confirm if you can hear me? Okay, fine. So I think, is it 1 minute? No. Now it's time. I'll start. So these were the questions, and I think I've gone very slow just to introduce the whole notion of fluid. And similar thing will apply for single fluid description of plasma, that you are dealing with a continuum and not individual particles. That is the main idea, so that you can write the equations in a form that one can at least handle the system. Otherwise, for individual particles, the argument was that it will become just too many number of equations that one cannot handle even on computers, supercomputers. These are just very basic physics of first law, second law of thermodynamics, and using your usual thermodynamics and writing the energy equation, which is often redundant for incompressible fluids. Okay, because the pressure can be completely determined. If I write this form here, you see this is an equation for three quantities. Yeah, this is a body force, which is a given thing, so that you can forget about. The only thing that we need to supply, and there is a density for which we anyway have an equation, which is continuity equation. Which in this case, suppose you assume constant density, so that is also dropped. That's kind of given. You don't have to evolve that. And pressure can be completely determined by taking a divergence of this equation, which will give you something like Laplacian of P in terms of the flow itself. Okay, so that gives you additional equations, and you don't need anything else to proceed to solutions. Okay. Now, it is very useful to actually come up with certain constants and properties in fluid, so that some intrinsic nature of the fluid one can determine. The equations, even if they look simple, they can be actually very formidable and challenging. And it is very useful to come up with quantities that are conserved. So while the fluid is moving, while the magnetic field is being generated, what are the quantities that remain invariant in time? This is the question that one will ask usually, and such conserved quantities basically constrain the dynamics of flow and magnetic fields and stuff. Okay. So knowing such conserved quantities can be very, very useful. Okay. That without even solving the full detailed equations, you can actually comment still a lot on the nature of fluids and flow. So let's for now assume a steady flow. By steady, one means the partial derivative of t with respect to t of any quantity is 0. So it's a steady flow. Okay. This is the usual Bernoulli's theorem. I will not spend too much time, but I'll just give you that. Take rho as a constant. Divergence of v is 0 from continuity equation. You can write down, use the vector identity to write down v dot nabla v term in terms of curl of v cross v plus a gradient type term. Okay, so it's a gradient type term which is v square by 2. Fine. So this is the quantity which is curl of v. You can imagine as vorticity. That's a quantity called vorticity omega, typically referred to as omega. But you write this term in the Euler equation like that. Okay. Steady, so this term goes away. This is not there. There was one gradient term which you can club with these two. Rho is constant, so you can pull it inside the gradient. So you can write gradient of p by rho and take a single gradient and combine the three terms that you will have. And you can write down a very simple equation which is v dot nabla of b. B is called a Bernoulli parameter or a Bernoulli function, you can say. So v dot nabla of b equals 0. It's a very important equation. That for a steady Euler's equation, this is the equation where b is p by rho plus kinetic energy, is a pressure term, kinetic energy plus gravitational potential per unit mass. Okay, the kinetic energy per unit mass. So like that. That means b is constant along a straight streamline. Okay. After all, this is a directional derivative. Yeah, it's a directional derivative. And this uh, essentially suggests, of course, it can have a different value on different streamlines, but for a given streamline that you integrate this curve of V, we are still not talking about turbulence or something, because turbulence is introduced only when you have viscosity. Right now, there is no such thing. Okay. So this is an Euler equation. So starting from the Euler equation, you know that there is a streamline. Yeah, it's like Vx by dx equal Vy by dy equal Vz by dz. If you solve such a thing, you get an equation of a streamline. And this Bernoulli number or Bernoulli function becomes a constant. And you have already seen applications of such things, that if you go why the thickness of the dam increases as depth and stuff like that. Those kind of questions you must have seen before. So I'll not spend too much time on that. That's a consequence of Bernoulli's theorem. And if you don't have gravity, for example, you know that as you increase the pressure, the velocity decreases and vice versa, right? All this Magnus theorem and stuff. So there's something that you must have studied in school much before. These are all coming from here. Okay? Furthermore, if suppose your fluid is irrotational, okay, what is irrotational? That is, the fluid is that curl of u v, or the so-called omega, is zero. It's a vector zero. If this is irrotational, then this term actually is zero, right? So then instead of this, you get basically the gradient of B equals zero. So that means B becomes uniform. Okay, it's a constant throughout the whole fluid. What does it mean? It's a very powerful thing. That means you are given a whole galaxy. Yeah, suppose I'm just basically exaggerating it. Suppose you are given a big object, very big object, for which this equation is valid. Okay, and you know the value of this number in one place at a single measurement, a single point. But if you know your conditions are such that this equation must be true, then you can extrapolate and say that, okay, this is the same number in every part of the system. Okay, that is the power of this. So you don't have to really solve for the whole thing. If you can solve or know at one place, you know everything. Similarly, in this case, along the streamline, if you know the value at one point in a straight line, in a streamline, then the whole streamline you basically can be extrapolated, because it's going to be conserved along the straight line, streamline. Okay, so that becomes very powerful. How do you know whether the fluid has? It's a very local property, vorticity. So suppose you put a ball in a fluid. Let's say you have a water, and if you want to test whether the fluid has vorticity or not, you put an arrow mark on a ball. Okay, you put draw an arrow mark, and if you put this into water, if this rotates, if that arrow that you drew has a rotation locally, wherever you put, you are not moving anything. You are just simply placing that ball as a test particle, marked test particle, so that you have drawn an axis of the test particle. So that test particle, if you drop in a fluid and the axis starts to rotate, then you will say that the fluid has vorticity. If the axis stays the same, you will say that the fluid has no vorticity. Okay, so you are testing the property of the fluid or nature of the fluid by simply dropping a test particle with an axis. Okay, so this is a very simple experiment in order to see if the fluid is rotational or irrotational. Okay. One example I'll come to very quickly. This is a very simple exercise, so I will not spend too much time. Another form, you can actually do a whole lot of things. Okay, you take the basically energy equation with internal energy term. Forget include gravity by yourself. Basically, you start from this equation. Yeah, steady means this term anyway has gone out. Okay, you can include gravity term, and you try to derive something like this. Okay, so there are various versions of this. Okay, so it's like P by rho plus U. H is enthalpy, right? So P by rho plus another internal energy term added. Anyway, one application very easy, as you know, that if you have say a river or ocean, this is the free surface. What is called a free surface is the interface between the liquid and air. Okay, it's an interface between the two fluids. One fluid is liquid, other is air above. Okay, so that's a free surface. Let's say it's a sea level at z equal to 0. You are only asked a question, how as a function of depth the pressure increases. We of course know that it increases, right? So how does it increase? What is the nature of increase? You take a constant density, like for water, the density itself is not varying as depth. Density is constant all throughout. Okay? So again, you know that the gravitational potential per unit mass in a plane parallel atmosphere, the gravity is pointing downward. This scalar g is larger than 0. The gravity is pointing downward. Yeah, stuff, usual things. That means the phi, this potential phi is basically gz. Yeah, there is only P by rho. There is no temperature here. It's an isothermal. There is no temperature in this case at the moment. P equal atmospheric pressure at Z equal to 0. So you basically immediately get a formula like that. That P as a function of Z is P naught minus rho Gz. Z is negative as you go down, right? Z equal to 0 is here. So basically, effectively, pressure is increasing as a function of depth. Okay, pressure at depth Z equal minus H is this number. All you have seen. Similarly, if there is a motion, so here this was a static fluid, right? This is like you are imagining a tub or a lake with no motion. So that's why there was no velocity appearing here and only a pressure distribution, and that you know from Bernoulli's theorem. Again, suppose there is a flow in a Venturi's tube, all these things you know. If this is very thickness is large, you can work out A1 V1 equal A2 V2. So velocity is very small here. Yeah, pressure is large, so that's why this tube has gone here. Here, as the cross section decreases, okay, as the cross section decreases, density is constant. Mass continuity equation is giving you rho A V equal constant, where A is the cross section. When A and rho is also a constant, that's why the area or a cross section times the velocity becomes a constant. As you go to a smaller cross section, your velocity increases. As your velocity increases, your pressure decreases. All that you can see from the Bernoulli's theorem. Okay, that's why the level in this tube, capillary, has gone only to a smaller level because the pressure is smaller here. Okay, similarly, that's a separate question. That why once you have come back to the same cross section here, the level is not exactly same as here. Okay, why is that? It's because the fluid here is not an ideal gas, and there are viscous effects. Energy is lost, and that energy loss is reflected in terms of a slightly smaller height. So this is from Feynman lectures, and you can read more in detail there. All right, so there is one very important application which you should all do for variety of background thermodynamics. I'll do it for isothermal background. Okay. So, for example, we know that in our atmosphere, gravity is of course pointing downward, right? The scalar g is positive, minus Ez, z is pointing upward, so minus Ez, gravity is pointing downward, that's a sign of gravity. Potential per unit mass is g times z, it's a plane parallel atmosphere, so everything is varying only along the z axis. There is no variation in x and y plane. Okay, x and y plane is like ground, and you are going up. Okay, you can ask the question, how does pressure changes as a function of height? Yeah, how does density vary as a function of height? Questions like these we can ask. Okay, but of course you have to supply an equation of the state that we know. What is this? This is an equation of state. And you have to choose your background, whether you are looking for an isothermal medium, that means is the whole layer of atmosphere has the same temperature, or it is adiabatic, or what is the background thermodynamics. For each of those, you will get different answers. Okay? So for other examples like adiabatic, you can try to work it out at home. Okay, equation of the state will remain the same. Let's just work out for an isothermal medium which is stratified under gravity. Okay, which is stratified under gravity. So T is equal to constant all throughout. It's a hydrostatic equilibrium. So vector V is 0. So it's a vector 0. So all components of velocity is 0. So whenever you will study eventually all these problems of instability or other kind of problems later on, for example, even the problem where I inverted the glass and everything fell down, Taylor instability and everything, or how the waves are generated, like as we speak, sound speed is propagating and stuff like that. So you have to know your 0th reference state. 0th reference state, it's always good to work out what is your hydrostatic equilibrium. Once you know your hydrostatic equilibrium, then you perturb it slightly and write down, linearize, and then write down the equations for perturbations and see what happens to those perturbations. If the perturbations evolve to grow in time, then you call that the system is unstable. If the perturbations evolve to decay in time, then you say that the system is stable. Okay? For example, convection, when you are boiling a teapot, this is unstable, right? Yeah, you perturb and then this just goes up and up and up. Yeah, you perturb in terms of you injected a lot of heat energy into a parcel of fluid. Your background stratification is such that it is super adiabatically stratified. So as the fluid parcel goes up, it is still lighter than the medium. Because the medium, you have worked out a background which is hydrostatic equilibrium of your background in which the perturbed particle is moving. So you can just ask such questions, right? But before you have done anything with your analysis, you have to know your hydrostatic equilibrium. So that's the must first step. So hydrostatic, of course, as the name speaks, equals 0. Euler equation, there is a gravity, there is a pressure term. So grad P plus rho grad phi is 0. Yeah. Gradient is only d by dz. So vectors drop out. So dp by dz is minus rho times g. Okay. Now you can use your equation of state. T is constant anyway, so it just becomes P is rho. So you can write dp by dz in terms of P here, which is obvious that this is a logarithmic function, right? So you solve this, use this. Rho is P by RT. RT is constant. So it just dp by dz is equal to minus some constant times P. So it's a exponentially decaying function. So that's the solution. So as you go above, z equal to 0 is the ground, and as you go above, the pressure decreases exponentially in an isothermal medium. So you see, pressure and density are decreasing exponentially such that the temperature remains constant all throughout. Okay. You determine two variables, third is automatically fixed from the equation of state. So that's why you don't have three things. Only two independent variables here. Once you solve, you find that the scale height, so-called scale height, when the pressure would have dropped to a value P naught by E, exponential of 1, P naught by E, that is called a layer of scale height, which for the Earth's atmosphere, you can work it out. It's roughly about 8 kilometers or 9 kilometers, 10 kilometers. You can take, R is gas constant, which is Boltzmann's constant divided by mean molecular weight, and the proton mass. So mean molecular weight for mixture of hydrogen, nitrogen, oxygen, nitrogen that we have is 29. That also you should be able to actually work out how to determine the mean molecular weight for a mixture of chemical molecules in air, such as the air. This is largely what? Oxygen and nitrogen. So what is the mean molecular weight of such a gas mixture? Actually, you may be asked to derive such a things in your various written tests and stuff like that. I just give you a number of elements. Yeah, you should be able to tell me what is the mean molecular. What is the formula for that? That will influence your gas constant here. Determine, for example, what is the atomic mass unit and stuff like that. So this sort of talk actually assumes that you know all this very elementary thermodynamics, which can actually be complicated enough. Okay. So use the value for room temperature and work out what is the scale height, the rough height within which the pressure does not change appreciably. So that means if I travel over a distance of a scale height, the pressure has not changed by drastic values. Okay. It's only after you have crossed a multiple scale height the pressure has changed drastically. Okay. Fine. There is a very important quantity which you can, if you think and imagine hard enough, you can try to understand all these hurricanes, volcanoes, hurricanes, and these various large-scale circulations that appear, tornadoes and stuff. Yeah? How do you understand? How should we understand these? Okay. So typically one appeals to conserved quantities again. Yeah, as I'll argue later on that viscosity for a bulk of the fluid far from boundaries can actually be ignored in a variety of contexts, and the fluid can be treated as an ideal where there is no viscosity, and all these things will be valid for an ideal fluid. So then again consider an ideal fluid, a barotropic fluid. A barotropic fluid is such where pressure is a function of density. Okay? Most fluids that you encounter are such fluids. Okay? Pressure is a function of density. If not, then you will have an additional term there, which will produce a seed vorticity. As I will also show later on for the magnetic field, that the vorticity equation looks very similar to the evolution of magnetic field equation, induction equation. Define vorticity as omega equal curl of V. You know an equation for V, which is an Euler equation. Take curl of that entire equation, basically this equation. Take curl of this equation, okay? Use the identity for V dot nabla V in terms of this. So curl of grad is 0 that you know, right? Use this identity and take curl. So curl of grad is 0. Okay, curl of grad is 0. For a constant density, you can just throw it. P is a function of rho, so this will not appear. That's where you need that barotropic fluid. Otherwise, you'll have a term which is grad P cross grad rho. If I take a curl here, you will have a term which is grad P cross grad rho. But if P is a function of rho, then grad P cross grad rho will always be 0. All that you can show. It's actually fairly straightforward. So for a barotropic fluid, you take curl of the Euler equation and you get such a simple looking equation. It's deceptively simple, but it's highly nonlinear equation. V is omega is curl of V, so it's a nonlinear equation. Okay. So vorticity evolves like this. Now you define a quantity which is more like an average circulation in a fluid. I have a medium, I have a fluid. Let's, for example, take motion of a flow in a bathtub or a tornado, yeah, and try to determine a circulation. So I can take a large enough, say, a loop and determine a line integral along the loop. That gives you circulation. Vorticity is a local property. Vorticity is a field quantity at a given point. Every point where there is velocity, you also have a vorticity at that point. Circulation is different. It's a measure of vorticity, you could say, in some sense. So you take a closed curve and determine the line integral along the closed curve of the flow. Yeah? Determine the line integral along a closed curve. Okay? It's a closed curve. If that number turns out to be non-zero, you will say the flow has circulation. Okay? And given that we do not have time at all, actually, I would say that you work it out if you are interested. The Kelvin circulation theorem. Okay? It's a very powerful theorem. Analog of that in MHD, magnetohydrodynamics, is Alfvén's flux freezing theorem. Okay, so these are very important two theorems which will come in handy. Derivation is not that difficult. In fact, you can do, but you have to be just careful that the curve is a material curve. What does it mean? That the curve that you are imagining in space is not an Eulerian curve. It's not a fixed curve. So curve itself is a function of time because there are fluid particles sitting on the curve. Fluid particles are in motion, but they are forming the closed curve. Okay? But they are themselves having a Lagrangian trajectory. They themselves can deform and go. So it's a time-dependent curve. That if you take care of that properly, then this is not very difficult to solve. You can show that the material derivative or a Lagrangian derivative of circulation is 0. So it's conserved. Okay. It's conserved in ideal fluid. Prove this. So this is goes by the name Kelvin circulation theorem. Okay. This implies that the vorticity through an area element, I can take this and write this in terms of curl of V, which is omega dot dA. So every closed curve will bound an area, right? So then I can also imagine this quantity, circulation, as a net flux of vorticity through an area enclosed by this curve CT. Okay, I hope this is clear. So every closed curve will have an area associated with it, and if I take apply again the Stokes theorem, I'll get curl of V dot dA. So in other words, the conservation of circulation implies that the vorticity is frozen to the fluid. That means that whatever is the flux of vorticity through the area element, this is conserved. So if I change the area element, because the curve can be deforming, I can just move it here or there or somewhere. The entire vorticity with the fluid will move with the fluid. Okay, it's frozen to the fluid. That is what is the statement. That means the vorticity, I may move the fluid, vorticity will not slip through it. Vorticity will move with the fluid. Okay. And it has amazing consequences, which you should just look up books or YouTube videos on circulation's theorem and stuff like that. Some very fascinating experiments can be done and are done to show the consequences of vorticity. It all is coming from here. Okay. Simple consequence I can show is a free vortex. Free vortex is something where you are not applying any external torque, okay, to maintain any circulation. You can imagine that you are dropping water at an edge in a bathtub away from the drainage. Okay, and you have always seen that there is some pattern that emerges. Okay, depending on your which hemisphere you are sitting, there is some pattern that emerges. Okay, because even if you just drop the liquid slowly, there is a Coriolis force that will, depending on the nature of the Coriolis force, depending on which hemisphere you're sitting, it will go in a cyclone or anticyclone. You know that in the northern hemisphere we have cyclones, and in southern we have an anticyclone. Yeah, the sense of rotation is determined by the global rotation of the Earth, which leads to the Coriolis forces on the body fluid, on the fluid in motion. But it's but just remember that the circulation now, as we just showed, is a constant. Far away from the center, which is say a drainage, okay, far away, you've just introduced a velocity or introduced a water. Okay, it might just go towards center with a radial velocity, but Coriolis force will push it sideways, so it will also have a v5 component. Anyway, if you draw a circular loop, so you can show that circle is basically 2 pi r, that's the line integral, 2 pi r, of along v5, which is say a constant along that. That must be a constant. So circulation is a constant. It's just like a conservation of angular moment r of momentum v. Okay, r times v5 is constant. We also know that suppose this is an incompressible fluid, so you can work out what is the radial component of that. That will also go as 1 over r. Total velocity, therefore, v will go as 1 over r. So as you might have noticed, as the fluid which is rotating, the same like say accretion disk, which is sucking material from the neighboring star, as material falls in, its angular momentum just goes on increasing as you go towards the center, right? Similar thing you have seen in the bathtub or a sink. Any sink, you will have seen that velocity just increases, spirals very, and there is even a singularity. At r equal to 0, the flow blows up. Okay, far away there is nothing. You can actually apply Bernoulli's theorem to work it out the free surface, because the fluid is moving very, very fast as it goes towards the center. The free surface is not a z equal to 0 layer. Okay? That's why this image is very important. So there is basically a throat here. Yeah, there is a throat here. Free surface, again, the definition of the free surface remains the same. Okay, there is a body which is rotating like that. There is a circulation here. That's a water, and that's a white is air. And this is the free surface which takes the form or shape minus 1 over r square. It's amazing, right? That as you go to the r equals 0, the z goes towards minus infinity. Yeah? If you were to look at this hurricane or this tornado from above, you would see a neck. Yeah? You would see a throat. There is nothing. There is basically only air. Because as the fluid is rotating very fast, the free surface then will be governed from the Bernoulli's theorem. Okay, but you must note that I have used the form B equal constant. When can I use B equal constant? I did not use V dot nabla B is constant. or 0. I said nabla B is 0, so B equal constant. Why did I use this? We are saying that there is a finite circulation, and yet we are saying that B is equal to constant, which is valid only for irrotational flow. Okay, so this is only a puzzle I'm finding. It's a very simple puzzle also. That if you in this flow, which looks like that there is a lot of rotation here like that, you can do that experiment actually in a sink. You take a test particle like a ball or a ping pong ball and you draw an arrow on that, put it in the body. You will find that at any given point, the ping pong ball will go like this, around this, and go inside like that, like that, like that, like that. But its axis will remain the same. The axis will not rotate. So it's a proof enough, and you can convince from many other ways, that the flow is irrotational. Free vortex is an example of fluid which is irrotational and has finite circulation. Okay, finite circulation only if you include the axis in the loop. So suppose I draw a loop without enclosing the axis, and I draw a loop here and determine circulation here. The circulation in this loop that does not include an axis, this axis, that circulation will vanish. This is a number which you will obtain only when your loop encloses the axis. Okay, so please note this. It's very important. So as far as the vorticity is concerned, this fluid, which looking like tornado and everything, it's actually irrotational. Okay, except at r equal to 0 where it is singular. Okay. Now, suppose there is a cloud moving by, you know that the hurricanes and all, they just move because there is a cloud, it's stuck to a cloud. As the cloud will move, it will drag this because the entire vorticity column or a vortex tube that it is forming, it will go like a solid body basically because it is frozen. So they will just go. Okay, they will basically be frozen to the fluid. Wherever you take the fluid, sorry, you will also carry the vorticity with it. Now, you can do actually something more. Okay, I don't know if I have put in somewhere. Yes, it's coming. There are these are known as Helmholtz vortex theorems, and you please look up much more in the textbooks. Vortex lines, they move with the fluid. So if by some reason I move the fluid, the vortex line will come with it. It will not dissipate. So examples, the fluid in mind here is the inversely incompressible fluid, constant density moving in presence of a conservative body force. Conservative body force, where you can express the force as a gradient of a potential. Those are conservative body force. Okay. So the quantity, which is circulation, which as you see, I have now already used the Stokes theorem to convert in terms of omega and dot ds, which is an area element enclosed by that closed loop. Okay, it's a flux of vorticity through that bounding surface, from that area element. So this is to be same for all cross sections of a vortex. So if I take a horizontal cut here and horizontal cut here, the width of the hurricane here and here are very different, right? Width is different. Vorticity will adjust itself such that the circulation remains conserved at these and these places. So it's very important. Why? Because then, as you can see immediately, it's also independent of time, that you consider a thin vortex tube, just consider a cylinder. Okay? So area element delta S times the length along the cylinder. Okay, so that is a constant. Okay, so this will imply that omega. Okay, now you put together all of this because this is anyway constant. Right? This is constant, mean omega dot ds is constant. Okay, why is this constant? Because mass conservation gives you this constant. Rho is constant anyway, right? Of constant density. Rho times area element delta S times small l, that's a total mass content in that channel. Rho is constant, so you can write delta S times L is a constant. From here, we know delta S times omega is a constant. So what does it mean? That omega goes as L. So If by any chance there is a cloud that comes and stretches this vortex tube, suppose I simply stretch the vortex tube, so the value of vorticity omega will simply increase with that. And remember, this is the omega when you are including the center axis. Okay, otherwise there is no rotation. So I hope you are following this point that I can simply stretch a vortex feed line and increase the vorticity. That means that's why this become very devastating, right? You must be hearing in news that hurricanes and tornadoes, they are very, very destructive and cause so much damage and stuff like that. Because something must have stretched it, and then the vorticity locally there has just blown up. Local vorticity increase meaning what? Very, very strong winds and everything. So it becomes very intense. Stretching of vortex tubes intensifies the local vorticity. And that is the reason that all this havoc that occurs at times. Okay. So as you see that these are all simple consequences of vortex theorem for ideal fluid. Now we'll very quickly introduce. Okay, I have already exhausted a lot of time, but anyway, I will just introduce viscosity as proportionality constant between a shear stress and a strain tensor, rate of strain. Okay, what is shear? If this is a solid surface, along x, if I have a fluid motion, the theorem is that the fluid motion as it reaches a solid boundary in presence of viscosity, the tangential velocity also must go to 0. So now there cannot be any slip of flow with the boundary. And the region in which this is decreasing sharply to become 0 from a finite in the bulk is called a boundary layer. Okay, so pictorially you can see if there is a wind blowing in the room, but you are very close to the wall, there will be a thin layer where the viscosity will become extremely important, and the fluid will come to the rest. That is the reason that your fan blade accumulates dust over time. Okay, fan is moving so fast. So if it was all ideal, why should the dust settle on the fan, which is just moving? Yeah? So the point is that as soon as the any particle, any fluid, anything touches the blade, which is a solid boundary, the relative motion goes to 0, no slip. So it sticks, and that's why your fan, the blade, this basically accumulates dust. Okay, so there is a thin boundary layer in which the viscosity is very, very important. Otherwise, in a large number of contexts, you can forget about viscosity in the bulk of the fluid. For example, bulk is where we are speaking standing away from the wall, that you can treat as a bulk, and you can usually deal with the usual ideal Euler equation. Tangential stress. So the pressure, of course, is no more isotropic. Okay, so in that all you can now think of, work it out later on. So you can have x component of the force and y component of the area. Okay, it's just like the velocity here is a velocity along x direction, but it varies along y. So that's a shear profile. Okay, so the stress that it leads to is proportional to the strain tensor. Strain tensor is exactly this cross derivative of v. X a component of velocity, y derivative. So that's basically a rate of strain, okay? Rate of stretching, you could say. At what rate you stretch? If you were to drop, say, a small particle, what is the rate at which you stress? It's also like a local vorticity, you can imagine. If there is such a profile, and if I drop now a body here, you can work out that it's applying a shear on the body, and that will basically lead to a rotation of that body. So locally, this simply means vorticity. This coefficient is called coefficient of dynamic viscosity. What typically one writes for equations is kinematic viscosity, which is eta by rho. Okay, I will not spend too much time, just give you a dimensional argument, and you read E.M. Purcell's article on life at lower Reynolds Sum. Very interesting article. Basically, this is a property of the fluid. Okay? This is not the property of body or anything else. This is a property of the medium, just like conductivity is a property of the conductor or wire. Viscosity is a property of the medium. Rho, density, is a density of fluid. So these both are property of the medium. You can construct a dimensionally a quantity which is eta square by rho, which has a dimension of force. So you can just look at that if at low enough Reynolds number, which I will define Reynolds number in a moment, where the viscosity term becomes more important. That means this term is the dominant term there, this type of term. This force determines all the dynamics basically. What does it mean? At low RE, the point is the inertia of the body will not matter. So that means if this number turns out to be, for example, water 10 to the minus 4 times, or in CGS units, is a very small number, suppose for water. So whether it's a basketball or whether it's a huge ship, okay, you will need exactly this much amount of force to move the two bodies. The size and mass of the body which is floating in the water does not matter at all. Okay, so that is the power of it, because this is entirely determined by the property of the fluid. And if this number is small, you will only require a very small force to push the body. Of course, so long as the Reynolds number is small. Okay, if your Reynolds number is large, so this will not work. But you can always make your Reynolds number very small by simply moving very slowly. Okay. So without the last term, we had already seen the derivation. What happens in presence of viscosity? You have a dissipative term added on the right hand side. So this is the kinematic viscosity, comes with a Laplacian. It's dissipative in nature. You can take very simple examples and show that this will dissipate the kinetic energy. Okay, you write down the equations and it will become clear. Incompressible fluid we are dealing with, so divergence of V is 0. Now you simply take, this is an inertial term, motion due to inertia. Okay? In an inertial term, this is a viscous term. If you simply compare these two terms of order, so this is of order V times V, which is V square divided by some length scale. This is nu times V divided by length scale square. So if you take the ratio of this with this order of magnitude, you get a control parameter called the Reynolds sum. Okay. So it is said that you take, for example, when someone is constructing a flight and one is making a miniature version of a flight in a lab, one tries to maintain the same Reynolds number. So if the Reynolds number is same, that's why it's called a control parameter. So long as you keep the Reynolds number same, then whatever else you change, like you take a small ship or a big ship, it doesn't matter. If the Reynolds numbers are same, the behavior is expected to be the same for that. Okay. Because this V is the velocity with which that body is moving. Okay. Fine. So this basically characterizes LV by nu. It's a dimensionless number that you can see. This characterizes whether the flow is going to be laminar or turbulent. Okay. Fine. I'll come to in a moment where what happens at nu equal to 0. It seems to suggest that this is a limit of infinite Reynolds number. So it seems to suggest that nu equal to 0 is like turbulent flow, which is when nu goes to 0. Although these are completely different things. Okay, nu equal to 0 and nu tending to 0, these are completely two different things. Solutions are not even close to each other in most cases. Okay, so that those are very subtle properties and things that you should be careful about when dealing with fluids. Inertial force versus viscous force. For various objects like the sun, the Reynolds number is very large, that means turbulent. Swimmer is not so small. When you are swimming in a body, in a pond, typical Reynolds number, because the viscosity of the water is not that high, it's actually small. So when this is small, this becomes larger. So you are actually at a typical Reynolds number is very large. It's only for the microorganisms, okay, some germs, something, microorganisms, that it can become very small. And these flows are known as Stokes flows, okay, which are reversible. And so I'll just show picture now for low Reynolds number flows. So this is the lowest Reynolds number, say 10 to the minus 2. This is a solid object, cylinder, where the cross section is like that. You can imagine a cylinder which is going inside the slide. Okay, this is a cross section, and there is a flow which is coming and hitting the cylinder. These are parallel flows coming from far distance. As it meets the obstacle, it deforms and goes around and just comes back. At low Reynolds number, you don't see any feature here. As you simply tune the Reynolds number, by tuning the Reynolds number larger, that means you simply increase, one thing you could do is simply increase the velocity of the flow. At 20, you already start to see vortices. See, we covered vortices for also one reason, that for turbulence, the vortices, they seem to be the quanta of vortices, basically like a building blocks of turbulence, quanta of turbulence. Because once you try to picture the turbulence, you'll find that they are made up of various large number of eddies and vorticities. Okay, so that's why understanding vorticities and circulation, this and that, can be very important, but we don't know. Okay. As you increase it further, you find that now there are braking and other types of vorticity forming, turbulence, motion is getting more and more chaotic. Many interesting things can happen, and you just look up references. At very high Reynolds number, which is 10 to the 6 that you can manage in the lab, suppose, it becomes totally turbulent, right? Very chaotic. So all these braking vortices that are forming, which does not happen here. The question I will ask you is, how does the flow look like in the inviscid case? Inviscid meaning infinite Reynolds number, one may argue. Okay? So does it go towards this direction or this direction? So the answer is, of course, that at a zero viscosity, inviscid case, it's close to the low, not high. Zero viscosity, the flow will look, basically the flow will come, that's a stagnation point, that's where the pressure is maximum, velocity is zero. Here, velocity is maximum, pressure is minimum. So pressure will decrease from maximum to minimum, again will reach a maximum. Flow will become exactly symmetric on the two sides. Here, symmetry is slightly broken. Okay, the profile is slightly broken symmetry at lower Reynolds number. At exactly zero viscosity, the so-called infinite Reynolds number, which many astrophysicists would like to claim, would like to call infinite Reynolds number limit, which is not true. Zero viscosity is just like laminar flow, laminar case. You will just have a flow which is exactly symmetric. Okay, and it will not have any of these turbulent characters. So all this is very important to please appreciate. Now I will very quickly come to plasma physics. I think I've just covered Navier-Stokes equation, a little bit small properties of this thing. If you change the Reynolds number, you go from Stokes to turbulent. In the regime of low Reynolds number, which is Stokes flow, you can see that the flow is reversible. Yeah? So if I make a flap 1, you move forward. Suppose you are swimming in a thick honey or something, such that the typical Reynolds number involved are very small. What will happen that you make some motion, you go forward, then you make a opposite motion, you come backward. Basically, you will not float or you will not move ahead. You have to do something more, the point is. Okay, so motions are reversible. Okay. Only for Stokes. Now let's come to plasma physics. But before that, just a little bit motivation. Okay? What is the motivation for studying this for us? At least the microscopic description. We know that in lab we see magnetic field on the scale of say a meter. Right? Magnetic fields we observe on all sorts of scales. Right? In the Earth, if you go, or see, these are the beautiful auroras, which are the northern lights that you can see from naked eye if you go towards the poles. Right? These are the auroras. Earth, the size you saw in the lab, you can have a bar magnet. If you go to the scale of the Earth, something like 10,000 kilometers, from 1 meter to 10,000, you still observe in space magnetic field. You go to the sun, which is 1,000 megameter. Yeah? So 1,000 into 10 to the 6 meter. So 10 to the 9 meters. So such a large object where there are these sunspots. One typical sunspot can be actually very larger than even the size of the Earth. Okay. So whatever was this 10,000 kilometer can be just a spot. On the whole global scale of the sun, which is 1,000 megameters, you still observe magnetic field. Not only that, There are times when the magnetic activity is very large, and I've covered in the solar physics, then it goes to solar minimum phase and then comes back. What is it that is driving and doing all this? Why the magnetic field is not only produced and has such wave-like pattern? What is causing this concentration of magnetic field, which is much larger scale than the granules or the convection scale, which is tiny oscillations that you see here in the image. These are the granular scales. These are the scales of convection at the photosphere, and the size of this active region is much larger than that. So what is maintaining that coherent, intense magnetic structure? It's dark because the convection is suppressed here, and that's why the region of sunspots or active region are cooler, have lower temperature than the surrounding. All this is something we know, but magnetic field seems very ubiquitous. Wherever you see, you find. You go between the sun and the earth, the interplanetary space, which is the distance of one astronomical unit, I think about 10 to 13 kilometers, you still see a magnetic field in the intervening space. Now you go to galactic scale, which is 10 kiloparsec scale. Yeah? It's huge, right? And you look at the image in the synchrotron, it's bright in synchrotron. Synchrotron is basically produced by what? You must have been taught in the radiative processes that there are electrons and charged particles gyrating in magnetic field lines and then producing the synchron radiation. So once you observe the synchrotron, so-called non-thermal radiation, it's a direct proof of the presence of magnetic field in all of the galaxies. Yeah. So regardless of where you observe in the universe, you always have magnetic field. So one goal many of us have is to understand what is producing these magnetic fields, what causes the magnetic fields in the universe. Okay. Then again you come back to very simple description of plasma physics. But how do you describe a plasma in a single fluid? Because we want to have a simple equation, as simple equation as possible, to understand as complicated and beautiful thing like a magnetic field on a whole range of scales. Okay, so that's important. So for us, the plasma will be a quasi-neutral mixture of ions and electrons that exhibit collective behavior. What is a collective behavior? That there are enough plus and minus charges, and you are seeing at scales large enough that in that scale, just like a unit parcel, there are enough plus and minus so that the effect of plus and minus is cancelled. That means the net electric field is cancelled. There is no charge separation to cause any electric field. Conductivity of the plasma is typically very high. So even if you create momentarily any charge separation, plus and minus, having electric field in between, they will just move and short out the electric field. But they cannot short out the magnetic field because there is no magnetic monopoles. Okay. You know the SAA ionization. I'll just speed up a bit so that tomorrow I can just complete in the first half and I don't have to take the second half. Second half is free. So you must have heard about SAA ionization equation. If not, look up. The ion number density, ratio of that to the neutral number density in a medium, is proportional to the temperature, because if you just take a neutral gas and start to heat up, what will happen? You heat the gas, basically electrons will come out and you have a soup of electrons and remaining positive charges. So ions and electrons are produced as you increase the temperature. These are the ionization potentials of that species. You can have a mixture of species. Okay. So, and this is also very interestingly shown here that as your ion, it's also inversely proportional to ion number density, right? Right. I forget what I wanted to say. Anyway, so just look up, try to plot this by the way. So that will be also very interesting. That how does this curve look like? Yeah, for some simple functions. We are focusing mainly on the space plasmas, which are nearly fully ionized plasmas. Okay, so there are hardly any neutrals in space. Okay, but just to complete one point, what I wanted to say is that even a very little bit of ionization is enough to actually drive currents, right? Because while your small parcel may have no net charge, the charges can be in motion. Plus and minus can move oppositely, and in this way they will produce a current. Every current will produce an associated magnetic field. So you can see, at least in principle, how it is possible to generate magnetic field if there is some motion in it. And it has to be self-sustained because the motions have to be self-sustained. Nobody is externally supplying any energy to produce the magnetic fields in a galaxy. It has to self-sustain all this process. Okay? So if there is a plasma and if they are in motion for some other mechanism, due to some other reasons, they are in motion, plasma charged particles in motion can produce currents, and that current will have associated magnetic fields. That may be one way. So that's one way to think of a so-called dynamo, where you are converting the energy from kinetic motions, converting it into magnetic motions, magnetic fields. Okay. So that's called dynamo, conversion of kinetic energy into magnetic energy. Okay. There is a very useful quantity called Debye length. So just like we argued for on the definition of fluids, the Debye length is simply a measure of a shielding distance. So that suppose I bring the plus charge here, it will attract negative charges around. So many negative charges. Suppose your plus ion is a big ion and negative charges are small negative ions will surround it. And if I look at distance, certain distance away, these negative charges would have completely shielded the positive charge, so that the net electric field here might vanish. So that's a reasonable way to think. The distance, okay, over which the shielding is effective, so that is the effective collective behavior of the plasma. That it is not a behavior of a single charge, but it's a behavior of a collection of particles, collection of charges. So if you are looking at distances of the order of a Debye length scale, the individual charges are completely screened out. Okay, so that's the distance. So we are actually interested for a single fluid description of plasma on a distances which are larger than the Debye length scale. So now you have another length scale to add to your list of scales. Okay. In the definition here, your mean free path, of course, must be still much smaller, but you must make sure that your unit cell has a large number of charged particles, so it's for the Debye length basically, yeah, a larger. Fine. So let's not discuss too much. You can construct quantities like plasma parameters should be very large, and plasma frequency. Basically, if I make a charge imbalance, they will short out because the plasma has a very high conductivity. So they will and they will oscillate. So if you are looking at time scales which are much larger than the inverse plasma frequency, the frequency of oscillation of charges basically, then you can forget about this oscillation also. So you are looking at a very slow dynamics. In a very slow dynamics, these oscillating charges or the effects of those can also be ignored. So we will be looking at average, slow, small, larger scale behavior on a slower time scales in a single fluid description. That's why it's also known as non-relativistic limit of plasma. So of course there are two approaches. One could study plasma in a particle picture and a fluid picture. In a particle picture we will not get into, but look at there are interest in studying the motion of individual charged particles. This can be very important. Of course, there is the plasma orbit theory, which is just like Newtonian physics in classical. This can be most accurately, but just that there are so many number of particles that you may not be able to handle for each charged particles, the orbits. Okay. But in some context, it can be very. For example, the fusion physics of plasma fusion, right? Fusion research, nuclear fusion. You have to have a plasma confinement, and you can look at examples like magnetic bottles and all, based on this orbit theory, that how the charged particles can be trapped by having a proper configuration of magnetic field, how the charged particles can be trapped, and those can motivate ways to confine the plasma before you can perform experiments of nuclear fusion and stuff. So it's a very useful approach. For us, we deal with fluid picture. Okay, if induced fields are significant, so orbit approach is often not suitable for studying the dynamics. So typical length scales are basically large, much larger than the Debye length scales, and typical time scales are very large compared to the inverse plasma frequency, so that the charge separation type effects can be totally ignored in a fluid like descriptions. Okay, that's the whole idea. I will. I think there is time is up. I will give you some break. But let me see if yes. So I will just complete this slide so that tomorrow I can actually then confidently complete the dynamo part. Okay. So the electrical conductivity of the plasma, it goes with a positive power of temperature. Quite obvious, right? That you have larger temperature, you have higher. It's by the way, it's opposite of viscosity. Viscosity is like a friction which increases, um, whereas conductivity is like inverse friction. Okay, but that also increases with temperature. Just think about it a bit carefully. Why? But simple answer is you need charges for conductivity. At higher temperature, there are more charges, more conductivity. Something very simple you can see. Okay. Now, once there are charges, there will be collisions, electron ion collisions, there will be resistivity, which is opposite of conductivity. Okay. So, microscopic resistivity goes as C square in the Gaussian CGS unit, C square by 4 pi sigma. It's inverse conductivity. Resistance in wire, for example. So, more like a resistivity of plasma, which goes as T to the minus 3 half. Okay. And this is the Ohm's law, from which you can determine the conductivity of the medium. It's a property of medium. If you apply an electric field, how fast the charges will move. That is, what is the response of the charged particle to an applied electric field. The proportionality constant will give you the conductivity of the plasma. Okay, so that can be measured. A very simple prescription like Ohm's law. Viscosity of a fluid goes like this. Okay. Because the species are contributing to momentum, like ions, they are heavy, so they contribute most to the momentum. Okay, that's why here there is an ion number density. Okay, so we can stop here, and I will request that you familiarize yourself a little bit more with the Maxwell's equations, and then I will very quickly derive an induction equation and show you an example of a large scale dynamo. How by small scale turbulence, by injecting energy at a very small scales, how can you produce magnetic fields over a large length scale? So it's an inverse cascade problem. How can you do? That will be the goal of my last lecture tomorrow morning. Okay. So thank you very much. If there are questions, I can try to read. So there is a question which I told immediately, right? How do you differentiate between vorticity and circulation? So it's obvious that vorticity is a property of a fluid at a given point, right? You are determining curl of velocity at a given point. Circulation is basically, you can think of this as a measure of vorticity in a net volume of a fluid or something. Yeah? Because it depends on that entire line integral. What circulation is more like not only the vorticity, but it's a flux of vorticity through an area. So it's more, it's an integral quantity. Okay, let's put it that way. Circulation is an integral quantity, which gives you a measure of flux of vorticity through an area element. Okay, that's omega dot dA. That is circulation. Okay. Vorticity itself is simply the curl of velocity. Okay, that is not integral quantity. I hope it is clear. Any other? I'll just wait a minute. If there is a question, you can either raise hand or chat. Otherwise, we'll meet tomorrow morning with dynamos.
Sir, this kind of large systems of interstellar gas or stars or like that, the magnetic field seems to be more important than the electric field.
That is right.
I mean, did you huge plasma? Is it have a huge amount of say electric fields as well?
No, that is right. That's a good question. The answer is very simple, which I partly answered, that the plasma has a very high conductivity. Okay, and charges can be plus and minus. Okay, there are mono charges, for example, plus charges or minus charges. So by any chance, electric field meaning there is some charge separation, and you can draw from plus charge to minus charge or minus charge to plus charge an electric field, right? What will happen that because of the conductivity J equal to sigma E, yeah, the charge separation will just be, the charges will run to each other. Okay, let's call it that way. Plus and minus separated, there is an electric field there. So if that electric field is present, plus and minus will come towards each other because they will attract. Conductivity is large, very quickly they will come and annihilate, and now the charges are mixed back again. Okay, once they are mixed, the electric field vanishes, right? Because they are shorted out. That is what you have shorted out the electric field. This you cannot do with magnetic field because there are no magnetic monopoles. Once you have a magnetic field, you have to live with it. You cannot get rid of it. Yeah. But of course, you can interpret electric field in terms of current and yeah. But I'm saying in a lab frame where there are charge separations, electric field in a lab frame, you can short it out. The electric field. That is why one doesn't talk about electric fields in the universe and only magnetic fields. And that's also why it is called magnetohydrodynamics and not electrohydrodynamics. Although, of course, you can relate electric field to magnetic field. Yeah. Or you can just call magnetic field an electric field. Because so just think of your relativity principles. We are going to the non-relativity relativistic part, but in special relativity, there is nothing like electric field or magnetic field. It's a frame dependent quantity. In one frame, what is electric field? In the other frame, it becomes magnetic field. Okay. But for us, it will be easy enough because there is a non-relativistic plasma. We will just call it there is no electric field, because as soon as you produce an electric field, that will drive some sort of a charge separation. But because of the high conductivity, the charges will come back to each other and they will short out. All this will happen over a time scale which is very short, say microsecond. But we are looking at time scale of galactic lifetime, which is what, giga year, right? So where is giga year and where is microsecond? Right? So that's the time scale difference. So while all this is happening, all this shortening and everything, we are not interested about that, those kind of time scales. Our interests are very, very slow. Giga year time scale, lifetime of a galaxy. Like this charge separation, like Debye length and all that, charge separation is happening over a scale of say centimeter or even micrometer. Galaxy has a size kiloparsec. So there is no point going to that small scale if you are interested only on the large scale slow behavior of the matter. Yeah. For other types of problem, you can go into a very large, small scales. For example, reconnection type problem, reconnection physics. But eventually the plasma or the fluid description at a very small length scale anyway breaks down. And in order to probe much deeper, higher resolution physics, you of course have to go to more advanced descriptions of medium, no more the fluid. But for various bulk properties and bulk behaviors, this is good enough. Yeah. Any other question or something? Okay, so I will discuss the problem of generation of large-scale magnetic field in various astrophysical objects tomorrow by looking at examples of or equations of magnetohydrodynamics. Thank you very much. See you tomorrow.